Hello! This video is the start of series that will help you to navigate the capabilities of the software for CNC machines programming SprutCAM. We'll show how easy and simple it is to form the technology for parts machining for various degrees of complexity and shape in SprutCAM step by step. We'll tell you about the user interface, external CAD systems integration, the equipment for which we'll develop and see code in our software. Historically, the feasibility of using CAM software in shops is directly related to the diversity of equipment used in these shops. At present, both machines from the 60s and high-tech 5-axis machining centers of the latest generation can work side by side. And if the first ones work in standard modes, modern machines are often equipped with high-speed spindles which allow high-speed machining, not only removing the metal, but also cladding and then machining it. Modern equipment doesn't always have special software for the NC code generation, and even if it has, the possibilities are limited by the complexity of parts. Older machines in general were not initially packed with special software. Because of this variety of CNC equipment, the need for an integrated workplace arises. SprutCAM software works with any modern CAD software capable of storing the output mathematical part model. This is ensured by the wide range of import formats in SprutCAM. Transferring a model between CAD and CAM systems can also be performed directly, bypassing the process of intermediate storage of the model. We talked about CAM systems in general. What are they used for? Now let's look at SprutCAM. We'll start from the beginning. In the main window we can observe the graphic window itself and the toolbars, which are located on the top and on the side. In the first drop-down panel we can see the information about the system, version, license which is currently installed, and the most important point here is settings. In the settings window we customize the system for ourselves. Here we can customize the user interface view to fit our needs, as well as here the project saving paths, 3D model files, parts blanks, import paths. Also, where the finished project and C code are saved and where the post-processes that we use are located. There are a lot of tabs and every separate parameter of the system is adjusted. After setup, we can save this configuration in the file, which we can load later. Next thing about the main panel is creating of a project, loading of an existing one, and saving of a project with a new name. This panel is responsible for enabling smart snaps. It allows to attach to individual nodes, 3D models, and flat drawings when moving any element. Next, there are two types of measurement tools. There is also a possibility to launch the post-processor and machining report. These two elements are responsible for access control. This item, the analysis of the rest material. And the last item is Tool-Rich Inspector. If we load tool adapter as a 3D model, then elements of this adapter will control are set here. That is about the upper panel. Also, there is a drop-down panel in which we can launch, for example, the Add-in Manager. In Add-in Manager, we can configure the integration with CAD and the information directly transferred from the CAD to the CAM. Also, here are duplicated some of the functions that we have already seen on the main panel, such as post-processor, reports, etc. The next element with question mark is all that is associated with help. Content help, knowledge base, welcome page in information system. Also here you can contact our support and launch the tutorial for self-mastering the system. The right panel is responsible for controlling the visibility of elements that are present in the working window. Show all. If we work, for example, with a lathe, we perform turning operations, you can make it visible by 3/4 so that you can see how the processing goes inside the part, for example, with internal drilling or boring. This controls the display of elements like shade, shade plus wire, wire, ambient occlusion. Here is the view management, top view, left and right views, isometric view. Next, a set of filters of individual geometric elements, for example, regarding the parts that we load. The first is to show all the geometry. This means that on the Model tab, all the geometry is the part itself. The 3D model of the workpiece, if it exists, also a 3D model of Ys, tacks, clumps, etc. Further, the visibility of the part. Next, visibility of job assignment. This is if we machine, for example, some separate surfaces in separate operations. Workpiece visibility. And the visibility of the result of machining. Visibility of the tool and adapter. Enable disable snap visibility, enable disable machine if it's chosen and we are not using the abstract scheme. Display of toolpaths in calculated operations, and the visibility of individual elements of the three-dimensional model itself, which we machine. For example, in this case, the visibility of points, segments, grids, surfaces, and edges. We looked at the interface. Further, I want to say about the principles of workflow in SprutCAM. The work is carried out in the order of the tabs. The first is the Model tab, where we load the necessary model for machining. We can also load a workpiece, snap. If necessary, we can draw any additional elements. For example, for simple drawings, which we will later use in machining, we can use the built-in 2D cut. We can enable it here. An additional item appears in an additional folder in the tree. Further, after we have loaded the model, if necessary, we can transform it. Move relative to the designed coordinate system, scale, copy. The next thing we do is switch to the machining tab, and in it, we are programming the machining process itself. We select the operation, fill in the parameters of the operation based on the modes, the tool, etc. And the last point is simulation. In this mode, we'll look at how the material is being machined. That is, how the tool moves, how the material is removed. This is the workflow of SprutCAM. We reviewed the general interface of the system, looked at locations of functions. Now let's perform the simple operation to see how the technological process in SprutCAM is programmed. We are on Simulation tab now. Let's go to Machining tab and see what do we have now. I mean, we have the CNC machine loaded. If we switch equipment, select the Machine tab, select the Generate 3-axis milling machine, then in the process we'll only see our part and tool. We'll not see the machine scheme, but in this example we'll choose the real CNC machine. Double-click on the machine, and on the second tab we select some 3-axis machine, just so that we can see and understand where we have the part regarding to the CNC machine table. The first thing we do is select the equipment, then switch to the Model tab. By default, the cursor is already on the Part tab. That means that SprutCAM is waiting for the part to be loaded. When we start SprutCAM, the cursor is usually located on this tab. Press the Import button, select a standard directory, for example 2.5D, and here choose a part with the name Part1 from IGS formats. Here we can also see which formats are available. The most common are, for example, IGS, STL, PostScript, DXF, STEP, etc. In this case, we are interested in Part 1. I'll select Part 1 and click the Open button. OK. Here we have the part loaded. If we select the catalog with elements of the part in the tree, we can see from which elements the part consists of. Here we have points and curves, as well as separate surfaces. Here we can use the filter that we watched in the first part of this video. For example, if we enable the ability to select only curves, you can select separate curves. These curves are located in the model means they were created by the designer in the process of designing this part. For example, if we enable the visibility of separate surfaces, only separate surfaces are available for selection. They can also be selected in the list respectively. They are highlighted in the window. That's what these filters are for, to be able to select one or another element. We've loaded the part. We will not load a separate 3D model of the workpiece and any snap-ins, tags, clamps, as we'll consider them in subsequent lessons. Let's go to the Machining tab and see how our part is located. It's located inside the table, because it was built in negative directions of the coordinate system. If the designer created it in the positive direction of the z-axis, then it would be located on the top of the table. If we turn off the visibility of the machine scheme, then we can see that our system automatically set the workpiece based on the maximum dimensions of the part along the axis. Of course, we always can set a custom workpiece. First of all, we can import it by setting a cursor on the workpiece and pressing the import button, or we can select any of the proposed primitives as the workpiece and adjust any parameter of it. Let's go back to the first settings tab and turn on the machine. We need to put the part and the workpiece on the top of the table of this machine. To do this, select the workpiece setup, press the button with 3 dots, and move along that axis. You can change the values using the mouse wheel, or you can enter manually. For example, let it be 100 mm. Click OK. Now we have moved the part and the workpiece to the top of the table. OK. What should we do next? We already have a part. There is a workpiece which is set by default by the system. There is G54. That is, the binding is also set by default. By default, it's the same as the designed coordinate system. And now we can create an operation. For example, choose Create, Roughing Waterline Operation, press Create. The tool has appeared. And even now we can press Start and we'll get the toolpath. It's highlighted in green. For better visibility, we can set the thickness of this path, means we can make it thicker so it's more observable. We loaded the part, we lifted it onto the machine table, pressed the Start, and now we already have a toolpath. This is a big advantage, that we don't need to fill a large number of parameters before we get any result of the path. We see the path and something might not suit us. For example, a step by Z. It's quite big here. We can fix it all later. So we looked at the finished path, determined things we are not satisfied, and begin to adjust the created operation. Select the tool, set the modes, correct the removal along Z-axis, correct the approach along the arc if necessary. We always see the result in simulation and how the material will be removed. To do this, switch to the Simulation tab. Here we include the machining result visibility. Here we see our part. Here is our machine scheme and tool. Let's make the speed of simulation a bit less. And here I'd like to add that there are several simulation modes. They are Solid, Voxel 3D, Voxel 5D, and Rock Solid. Let's look at the example of Voxel 5D. It's fast enough and high quality. Press Simulation. It can be noted that in those places where the tool touches the material, the color changes so that we can imagine where, at what stage, at what operation, and with what tool a particular element is machined. As you can see here, our block lights up on the Z-axis. Most likely at this machine. Z-axis doesn't allow the spindle to fall lower. In this case, we need to either choose a longer tool or set an additional holder. That's what the machine scheme is for. Return to Machining tab. Here we see that there are borders registered in the scheme. Now we can observe that we move the table along x-axis and at some point it starts to turn red. That means that we go beyond the limit switches of the circuit. Each machine has its own limits on the working parts. As you can see along z-axis, it also turns red at a certain value. We can avoid this error. Here we see an exclamation mark. This can always be corrected. For example, to make setting of the part higher means to add some kind of fixture. Double-click on operation. This is our tool. It has a length and we'll choose a holder for it from the standard ones. As you can see, the holder increases the tool overhang. Press Run. In our case, we'll lock this distance. Let's go back to the machine scheme. Select the workpiece setup and for Z, set for example 120 mm. Let's check. Press Yes and Run. See where is the error now. This can be seen at the modeling stage right here. An exclamation mark is set. Hovering the mouse point on the operation, we'll see information about the error. It's written Contact with model on Rapid Fit. Good. Actually, for this we need a modeling mode in which we can understand what is going wrong here and correct it. Switch to machining. Stand on operation, double-click on the operation. In the parameters, there are approaches and retract. This is our third tab, lead in, lead out. Let's make an approach by the arc. Okay, now calculate the operation. As you can see now it's ticked. Go to Simulation tab. Press Reset and Run. As you can see now we have no mistakes. Thus we are machining. What can we fix else? As already mentioned, we created the operation spontaneously. The tool was selected by the system by default from the library that is currently connected. You'll have your own tool, your own parameters and cutting speeds. Let's fix one more parameter. For example, the height of removal material. Open the options. Here we have parameters tab. By default, we have 25 mm for one layer. Change this value to 5. So we'll have 13 layers. The system recalculated based on the workpiece. Click OK. Run. The toolpath is calculated. Now the distance between the layers is 5 mm. Switch to simulation. Reset and run smooth modeling. You can always click Simulate All and see the result of machining. Look now, when the scheme works, the part is moving relative to the tool. The tool is in place. If you turn off the visibility of the scheme, then we'll observe our workpiece and the tool that moves around it. That's all. Now we have created the simplest operation, changed a couple of parameters and obtained the processing of our detail. Later, of course, we change the parameters and adjust to what we need. This is how the system works.